First fact. A black hole is an area of space with gravity so intense that its edge is impassable even for light. This edge is known as the event horizon. Everything within it loses its cause and effect link to the external universe. The radius is determined solely by mass, not density, and is calculated using the Schwarzschild formula R equals 2gm by c squared. Hypothetically, the Sun's event horizon would measure about 3 kilometers, while Earth's would be roughly 9 millimeters. Crucially, black holes do not suck in the cosmos. An object on a safe orbit will maintain stable rotation, just as it would around any other mass. Time slows down near the horizon. This is gravitational time dilation, and light undergoes a strong redshift. An observer far away will never witness an object crossing the horizon. Its image will appear to freeze and dim until it vanishes. The second fact is that the most dependable method for a black hole's birth is the collapse of the core of an extremely massive star once its thermonuclear fuel runs out. At this point, the pressure from degenerate gas and neutrons is insufficient to hold up the weight of the outer layers, and gravity prevails. The outcome, whether a supernova or a silent direct collapse into a black hole, depends on the star's mass and composition. The critical masses are influenced by metallicity and mass lost through stellar winds. It is estimated that the initial star needs to be tens of solar masses, and the core that remains should be around 2 to 3 solar masses. In systems with 2 stars, fallback can occur, meaning some expelled material comes back, adding to the mass of the newly created hole. This type of evolution accounts for the presence of numerous X-ray binary systems.
Факт 3. At центрах most major galaxy lie supermassive black holes з масами от мільйонів до 10 біліонів solar mass. Наша own Milky Way galaxy hosted Sagittarius A at your core, weighing around 4 мільйони solar mass. Її існуювання верифіцировано по орбітам стар, викиси whichever years of study form stretched ellipses around an unseen center. Галаксія М87 contain a supermassive black hole з масою roughly 6,5 біліонів solar mass, powering a massive jet. The Event Horizon Telescope achieved the first image of such a black hole's shadow. This image shows a dark area against a bright accretion flow, directly supporting the general relativistic model. These observations record not an absence of data, but a gravitational shadow, an area from which light has the lowest probability of reaching us. Факт 3. Супермасів блекхоли з масами спанінг мільйони до 10 біліонів solar mass хидані в центрах most large галаксії. Децентральний об'єкт в Milky Way, Sagittarius A, має масу около 4 мільйони solar mass. Його присутність підтверджено по орбітам стар, викиси whichever years of observation draw elongated ellipses around an invisible center. В М87 галактики супермасіва хола розічся около 6,5 біліонів solar mass і пауери Giant Jet. The Event Horizon Telescope obtained the first image of such a hole's shadow, a dark spot against a glowing accretion flow, which provided direct confirmation of the general relativistic picture. These observations capture not a gap in the image, but a gravitational shadow, a region from which light has the least likely to reach us.
The fourth fact states that quantum field theory predicts black holes emit radiation on a curved background, referred to as Hawking radiation. From the perspective of an outside observer, the hole appears to have a temperature that is inversely related to its mass. Smaller black holes are hotter, while larger ones are nearly cold. For an object with stellar mass, the temperature is minuscule, significantly lower than the cosmic microwave background radiation, rendering this emission currently elusive. Theoretically, a black hole is expected to evaporate by losing mass, and its lifespan increases with the cube of its mass. Supermassive black holes will persist for a duration far exceeding the universe's present age. The underlying process involves quantum fluctuations that arise near the event horizon, yet the specifics of the information paradox, the challenge of aligning quantum unitarity with evaporation, continue to be areas of vigorous investigation and discussion. The fifth fact is about matter approaching a black hole. As it falls, it creates a hot accretion disk. Friction and magnetic fields heat the gas to millions of degrees, making it emit X-rays and ultraviolet light. The efficiency of this gravitational power station in converting mass to energy is immense. For a fast-spinning Kerr black hole, this efficiency can be around tens of percent, which is better than nuclear fusion. Plasma streams are ejected along the rotation axis at speeds near the speed of light, forming jets. One explanation is the extraction of rotational energy via magnetic fields pulled taut by the ergosphere. The brightness is capped by radiation pressure, known as the Eddington limit. If the disk becomes too bright, the radiation will push the gas outwards, regulating how much material the central object consumes. The sixth fact concerns the rotating black hole, known as the Kerr solution. This black hole features a distinct area beyond its event horizon termed the ergosphere. Inside the ergosphere, space-time is caught up in the rotation, compelling even light to move along with the overall swirl, unable to remain still relative to far-off stars. It's important to note that the ergosphere is not the horizon itself. Exiting it is still feasible. However, any world line within it is compelled to rotate in the direction of the spin. The Penrose process leverages this feature. A particle breaks apart within the ergosphere, with one part descending past the horizon, carrying negative energy, as perceived by an observer at infinity, while the other part escapes, possessing more energy than the initial particle. In theory, immense amounts of energy can be drawn from this rotation, up to approximately 29% of the mass energy of an extreme black hole. This positions the ergosphere as a cosmic flywheel, though it is exceptionally hard to reach. Seventh fact: the radius of the innermost stable circular orbit, known as ISCO, sets the inner limit for safe orbital motion within the disk. For a non-rotating Schwarzschild black hole, ISCO is situated at 6 gm by c squared, equivalent to 3 Schwarzschild radii. For a Kerr black hole spinning at its maximum rate with prograde movement, ISCO moves to a position very near the event horizon. This change affects the energy conversion process during accretion. The proportion of mass turned into radiation rises from roughly 5 to 6% for the Schwarzschild type to a theoretical 40% for the extremely fast-spinning type. Astronomers determine black hole spins by examining their X-ray spectra. Techniques such as studying the reflection from the inner disk and employing continuum fitting lead to the conclusion that certain black holes found in binary systems and at the cores of galaxies are rotating with a parameter A star that is nearly 1. This observation is consistent with the high performance and brightness of their accretion mechanisms. The eighth fact is about the photon sphere, which exists around a black hole. At a distance of 3 gm/c squared in the Schwarzschild scenario, light can orbit. However, even a small disturbance causes light to either escape or fall inward. The significant warping of spacetime creates what an observer perceives as a gravitational shadow. For a non-rotating black hole, this shadow's diameter is approximately 5.2 Schwarzschild radii. For a rotating black hole, this diameter is slightly altered and displaced. In actuality, the shadow is encircled by a luminous photon ring, composed of light rays that have made numerous circuits around the object. Doppler boosting causes one side of the ring to appear brighter as gas from the disk is moving towards us. This very contrast was detected by the interferometers of the Event Horizon Telescope project. It's not a void in light, but an area from which rays barely reach us, ensnared by the extreme geometry of spacetime and consumed by the horizon. Fact 9. Spaghettification is a real phenomenon, not a metaphor, caused by tidal forces. This means the gravitational pull is different on your head compared to your feet, stretching and squeezing you. For black holes formed from stars, this force difference is extreme and lethal well before you reach the event horizon. Supermassive black holes, on the other hand, have a smoother field gradient at their horizon. This allows an astronaut, if they ignore radiation and magnetic disturbances, to pass the boundary without immediate catastrophic effects. The ultimate demise would happen later, closer to the singularity. If a whole star gets too close to a central black hole, it can be torn apart by tidal forces. The star breaks, with half its matter being ejected and the other half returning. This process creates an ultraviolet X-ray burst and a typical decrease in brightness, roughly following T to the -5/3. These tidal disruption events have been observed numerous times and act as indicators of these hidden massive objects. 11th fact. When black holes merge, they disturb the structure of space-time, creating gravitational waves. These waves are minute distortions, stretching and compressing, measuring only fractions of a proton across distances of a kilometer. In the year 2015, the initial signal from a binary black hole merger, designated GW150914, was recorded. This signal was marked by a gradual rise in both frequency and amplitude, known as a chirp. The event culminated in the unification of two objects, each possessing a mass comparable to several tens of solar masses, into a single black hole. Over an extremely brief period, mere fractions of a second, a substantial amount of energy was released, equivalent to 3 solar masses in their pure energetic form. Subsequently, the LIGO and Virgo detectors have registered numerous similar occurrences, with the collected data enabling analysis of the varied masses and spins of black holes. These findings serve not only to validate the principles of general relativity under intense gravitational conditions, but also to illuminate the formation pathways of binary black hole systems. Two primary hypotheses are considered. Either they initially form as tight binary stellar systems, or they subsequently encounter one another within dense stellar clusters, where gravitational interactions facilitate their union. The 11th fact is that the story of black holes started well before the phrase itself was coined. In 1916, Carl Schwarzschild derived the first precise solution to Einstein's equations for a mass with spherical symmetry. In 1939, Oppenheimer and Snyder demonstrated that a star core that is heavy enough will unavoidably collapse. The Chandrasekhar limit, approximately 1.4 times the mass of the Sun, marked the distinction between white dwarfs and supernovae. Following this, the Oppenheimer-Volkoff limit, which is in the range of 2 to 3 solar masses, differentiated neutron stars from black holes. John Wheeler established the term black hole in the late 1960s, though it had been seen in the media before. From that point, the concept emerged from theoretical shadows. During the 1970s, Bekenstein established a connection between the horizon's area and entropy, and Hawking predicted quantum evaporation. This changed black holes from being cold graves into thermodynamic entities. Over time, the understanding expanded to include the ergosphere, shadow, radiation, and gravitational waves, turning the hypothesis into something that could be observed. The 12th fact is that searching for black holes relies on a collection of sophisticated indirect techniques. In X-ray binary systems, such as Cygnus X1, the unseen companion draws gas from an adjacent star. This hot accretion stream radiates in the hard energy range, and by analyzing the motions of the luminous donor star, astronomers can calculate the dynamic mass of the invisible object. Should this mass surpass the established thresholds for neutron stars, it is considered a strong indication of a black hole. For the centers of galaxies, mass estimations are derived from the velocities of stars and gas, as well as from the phenomenon of reverberation, which is the lagged reaction of broad emission lines to fluctuations in the accretion disk.
The gravity interferometer monitored the star S2 as it orbited the center of the Milky Way and detected gravitational redshift at its closest point, thereby validating the presence of a supermassive object. The Event Horizon Telescope Initiative connected radio telescopes globally to capture the shadow, first of M87 star, followed by Sagittarius A star. These images serve as visual evidence of extreme gravitational forces rather than mere voids in light. 13th fact. One persistent myth claims that a black hole sucks up everything nearby, annihilating galaxies. In truth, its gravitational pull adheres to the same principles. At far orbits, it acts like any regular mass, allowing planets or stars to maintain stable paths, provided they do not enter an area where stability ceases. Another common apprehension is about many-holes, potentially created by colliders. Yet, cosmic rays possessing energies exceeding those of accelerators have been impacting Earth and stars for billions of years. If such minuscule objects were formed and persisted, their consequences would be observable. Moreover, theoretical models suggest that these supposed tiny holes dissipate very rapidly via Hawking radiation. The notion that everything will ultimately end up in a hole is also inaccurate. The universe's development involves expansion. The breakdown of baryons is uncertain, and dark energy's thermodynamics are considered. Numerous outcomes are possible, and a devouring end is neither the sole nor a confirmed destiny. The 14th fact highlights the impressive scale and speeds of black holes. Supermassive black holes found in quasars from the early universe only a few 100 million years after the Big Bang had already reached masses of hundreds of millions of solar masses or higher. This poses a puzzle about their rapid formation, with explanations including seeds from direct collapse of gas clouds, fast growth during super-Eddington accretion events, and frequent mergers. The Schwarzschild radius of the giant M87 star is tens of astronomical units, comparable to Pluto's orbit in our solar system. Despite this size, its entire mass is contained within a region that light cannot escape. On the lighter end of the spectrum are stellar mass black holes. In binary systems, their masses are estimated to be a few to tens of solar masses. Furthermore, the spins of some of these, indicated by spectral and relativistic evidence, are near their maximum possible values. Even quiet supermassive black holes, such as our own SGR-A star, occasionally emit flares when a random amount of gas enters their central region. Fact number 15. The aesthetic of the gravitational abyss was rapidly embraced by culture. In Interstellar, the depiction of a black hole was based on calculations supervised by Kip Thorne. Rays were tracked through warped spacetime, resulting in the disk being visible not just from its flat side, but also from above, as light wraps around the hole, creating a halo. The movie made minor adjustments to brightness variations and colors for better viewer clarity, but the core ideas of the photon ring and Doppler enhancement from incoming gas are grounded in actual physics. The extent of time slowing on a planet situated near the horizon is a point of contention in the film. For a single hour to equate to years, conditions would have to be extreme, making a stable orbit and surviving tidal forces highly improbable. Despite this, the film accomplished a notable feat. It introduced precise mathematics into major filmmaking and offered viewers a visual representation akin to what current interferometers generate. The 16th fact addresses the relativistic dragging of spacetime due to rotation, termed the Lenz-Thirring effect. This phenomenon causes particle and gas clump orbits to precess around a black hole's axis. Near the event horizon, it results in the Bardeen-Pedersen effect, where inner disk layers align with the spin's equatorial plane while outer layers stay tilted. This creates a distorted flow geometry. Such warping changes jet direction and may account for gradual jet bends across scales from astronomical units to parsecs. In X-ray systems, precession appears as quasi-periodic oscillations, which are faint yet steady brightness fluctuations on millisecond to second timescales.
Their frequencies, tied to mass and spin, act as indirect clocks for strong gravity. By correlating various oscillation modes, scientists aim to map the geometry of the region near the horizon without direct visual representation. 17th fact. Black holes do more than just consume. They also shape their environments via feedback. The energy released by accretion and jets heats and pushes gas away, which in turn inhibits star formation at galactic centers. Within the hot gas of clusters, empty spaces, known as cavitation bubbles, can be seen. These bubbles are inflated by the jets emanating from active nuclei and are lit up by the X-ray emission from the nearby plasma. This process, working against gravitational cooling, provides an explanation for why massive elliptical galaxies are frequently red and dead instead of vigorously creating stars. The masses of central black holes are found to be correlated with the characteristics of the bulge, such as the dispersion of stellar velocities and luminosity, suggesting a shared evolutionary path. When a nucleus becomes active, it appears as a quasar, characterized by extreme luminosity due to high accretion rates, featuring both broad and narrow spectral lines and exhibiting variability in its output over periods ranging from days to years. Once the available fuel is depleted, the nucleus idles, but evidence of its former active periods, such as shock fronts and chemical enrichment, continue to be discernible in the interstellar environment for an extended duration. The 18th fact states that black holes have thermodynamics. The established laws of black hole mechanics are formally similar to common laws. Surface gravity functions as temperature. The event horizon's area is analogous to entropy, and mass is akin to internal energy. Bekenstein initially hypothesized that entropy is directly proportional to area, and Hawking determined the proportionality constant. 1 bit of randomness corresponds to each quarter of the area measured in Planck units. From this, a remarkable deduction emerges. A black hole is the most information-dense object by volume. Nevertheless, the question of how this information vanishes or is retained during the evaporation process is unresolved and is termed the information paradox. Proposed models include soft hair, gravitational replication effects, holography, and firewalls, yet agreement is lacking. It is conscientiously pointed out that this is a developing field in theory, where strict mathematical findings and observable implications are currently infrequent and necessitate cautious interpretation. Fact 19. Accretion exhibits diversity. The standard Shakura-Sunyaev thin disk is characterized as cold, geometrically thin, and highly efficient in radiation. Nearly all gravitational energy is emitted as light. Conversely, at low accretion rates, a tenuous hot flow emerges, which is radiatively inefficient, RIAF/ADAF. Within this flow, energy is transported internally, and the spectrum hardens into the X-ray range. In X-ray binary systems, these regimes interchange. The soft state is primarily driven by the disk's thermal emission, whereas the hard state is defined by a corona of hot electrons that Compton scatter soft photons. The transitions between these states are associated with the switching on or off of compact jets, demonstrating a connection between the disk, corona, and jets. A fundamental plane of activity has been noted. The mass, X-ray, and radioluminosity of objects, spanning from stellar mass to supermassive scales, conform to a unified scaling law, highlighting the universal nature of accretion physics. Fact 20. Primordial black holes are hypothetical objects believed to have originated not from stars, but from dense fluctuations in the early universe. Their masses could have varied from asteroid-like to stellar and greater. In recent years, discussions have focused on whether these objects could make up a notable portion of dark matter or account for some gravitational wave sources. Nevertheless, strict limitations exist. Stellar microlensing, gamma-ray background from small black hole evaporation, star cluster dynamics, and cosmological data significantly restrict the permissible mass ranges. Current observational signs do not offer a conclusive answer, leaving the scenario contentious. It's possible that some LIGO/Virgo events are connected to primordial holes or entirely to the stellar formation pathway. It is correct to state that this is an elegant concept bridging cosmology and astrophysics, still awaiting definitive testing. Fact 21. Gravitational lensing serves as a quiet indicator of a black hole, as its gravitational field bends the rays of light from a far-off star or galaxy. Powerful lensing can form an Einstein ring or spread a source into arcs. However, for individual stellar mass objects, less significant effects are typically observed. A brief increase in brightness, microlensing, and a minute displacement in the apparent position of the background object, an astrometric trail measured in billionths of an arcsecond. It is through this method that telescopes such as Hubble and Gaia have recently reported potential isolated black holes. The light from distant stars acted over days and months as if an unseen mass equivalent to several suns was drawing it in. The value of this technique lies in its independence from accretion and X-rays. It enables the study of objects that would otherwise be entirely concealed, providing a rare chance to determine the mass of the galaxy's dormant gravitational structures. Fact 22nd. The theorem known as no hair asserts that a stationary, isolated black hole within general relativity is fully characterized by three properties: its mass, spin, and electric charge. In actual astrophysical conditions, the electric charge is quickly neutralized by the surrounding plasma, leaving behind only mass and spin. Consequently, the state of a black hole after a merger is highly predictable. The newly formed hole should emit a set of quasi-normal modes, akin to a space-time bell ringing with precisely determinable frequencies and decay rates. Gravitational wave detectors are designed to detect these overtones, enabling black hole spectroscopy and the verification of Kerr geometry to ascertain if the observed frequencies align with theoretical ones. Although measurement errors are presently significant, initial indications suggest agreement with the theory. Any consistent deviations would constitute a major discovery, implying either the actual presence of hair at the event horizon or the necessity for a new physical framework that extends beyond general relativity. Fact 23rd. Magnetic fields act as the concealed armature for accretion engines. Measurements of light polarization taken with event horizon interferometers have revealed organized structures around M87 star close to its shadow. These fields are wound like hoops and spokes, guiding plasma toward the poles. Within this setting, a magnetically arrested disk, MAD, mode can operate. In this mode, the inflowing plasma stream carries a substantial amount of magnetic flux, which impedes its continued fall toward the black hole while concurrently supplying the jet. The Blandford-Zeineck mechanism taps into the black hole's rotational energy via these fields, functioning as a vast electromagnetic generator. The observed relationships between radio brightness, polarization, and jet strength corroborate this model. A greater magnetic supply and faster spin result in a more consistent and luminous jet capable of penetrating interstellar space over thousands of light-years. Fact 24th. Intermediate black holes serve as the missing connection between stellar and supermassive black holes, possessing masses from hundreds to hundreds of thousands of solar masses. Their presence is logical for models explaining the growth of galactic behemoths, yet observations are scarce and inconclusive. Potential candidates appear as extremely bright X-ray sources on the outskirts of galaxies, where standard accretion processes find it difficult to produce such luminosity without additional mass. Additionally, there are dynamic clues within dense globular clusters. Stars orbit as if an unseen massive object resides at their core. Gravitational wave events resulting in objects with masses of about 100 solar masses also support the concept of hierarchical mergers, where black holes form, merge, and then recouple. Currently, this is a collection of circumstantial evidence, but if intermediate mass black holes are verified, they will act as the natural beginnings for early quasars. The 25th fact states that the universe, based on current information, has a background of nanohertz gravitational waves. This is an extremely low-frequency hum. Interpretations suggest it is generated by pairs of supermassive black holes in galaxies that are merging. Laser interferometers cannot detect these frequencies because they are too low. Instead, millisecond pulsars, which are highly accurate beacons, are used as clocks. When space-time slightly rises or falls, the arrival times of pulses from these pulsars shift in sync across the sky. International projects focused on timing pulsars have announced statistical signs of this background. The signal shows the necessary angular correlation and a spectrum that matches predictions for a large collection of galactic centers undergoing different phases of spiral approach. This is not one loud burst as with LIGO, but rather the collective quiet murmur of a billion distant interactions, providing insight into how galaxies and their massive black cores have grown. Fact 26. The merger of two black holes results in gravitational waves that transport both energy and momentum. If the emission is uneven due to differences in mass or spin alignment, the resulting black hole experiences a directed impulse termed a gravitational kick. According to calculations and simulations, this kick can impart velocities of thousands of kilometers per second, although speeds in the hundreds of kilometers per second are more frequently observed. For supermassive black holes situated at the centers of galaxies, this phenomenon is significant because such velocities can overcome gravitational binding, potentially causing the object to move away from the galactic nucleus or even be expelled into the halo. Astronomers are actively looking for active galactic nuclei exhibiting displacement, along with asymmetric emission lines and quasars showing apparent shifts relative to the stellar center, which could indicate the presence of gravitational kicks. The period preceding the merger also leaves distinct signatures. A binary black hole can expel stars, forming nuclei with a shattered appearance. Following the kick, it may drag a dense collection of stars known as a hypercompact cluster, which remains gravitationally tethered to the escaping object. The 27th fact. A black hole's consumption in a quiescent galaxy is characterized by infrequent tidal stellar disruptions. It's estimated that in a typical galaxy, such an event happens roughly once every 10,000 to 100,000 years. This occurs when a star ventures too close, is ripped apart by tidal forces, with some material scattering away and some falling back, creating a flare that shows a typical luminosity drop described by T to the power of -5/3. Some instances involve jetted events, where a focused stream is generated and the signal reaches the gamma and X-ray bands. Other instances are optically thick, where winds process most of the energy and emit it in ultraviolet and optical light. An infrared echo reflection from dust heated around the nucleus is frequently observed. Partial disruptions also occur, where a star is partially damaged and then resumes an eccentric orbit, producing intermittent flares. These varied patterns aid in indirectly determining the masses and rotation rates of concealed massive objects and in understanding gas circulation and energy loss near the event horizon. Fact 28. The relativistically distorted iron K-alpha line serves as a reliable indicator of spin. In a resting atom, this line is found around 6.4 keV. However, light near the event horizon undergoes gravitational redshift, Doppler broadening, and aberration. This leads to an asymmetric, saw-like shape with a broadened red wing that can reach several keV. Current X-ray observatories can currently measure this line and a reflection hump between 20 and 30 keV. They also detect the time lags between coronal changes and the disk's reaction, known as reverberation, which can range from milliseconds to hours. By correlating the line's shape, the delays, and the continuum, scientists model the inner disk's location, which is connected to ISCO, and thus determine the spin. While this method benefits from robust statistics, it is susceptible to systematic errors, such as corona geometry, disk ionization, and absorption along the light path. Consequently, spin values are verified using multiple independent methods. Agreement across these methods is sought before making conclusions about how fast a particular black hole is spinning. Fact 29th. The growth of a supermassive black hole requires a galaxy to funnel a substantial amount of cold gas towards its center and reduce its angular momentum. This process is facilitated by galaxy mergers, bar-and-bar structures, spiral instabilities, and turbulent accretion from the intergalactic environment. Within the galactic nucleus, the gas compresses, leading to star formation and concurrent feeding of the accretion disk. A portion of the core's light is obscured by dense dust and gas, forming a torus. Observations made along the plane of this torus reveal Type II characteristics, narrow emission lines, while observations from a perpendicular angle show Type I characteristics, broad emission lines. This unifying model is further refined by evolutionary considerations. Numerous galactic nuclei are so deeply obscured, Compton thick, that their influence is detectable only in hard X-ray emissions and the cosmic X-ray background. The peak of this background radiation is attributed to the collective emission from numerous concealed active galactic nuclei. The activity of these black holes is episodic, following a duty cycle pattern. Brief periods of intense activity, lasting from hundreds of thousands to millions of years by cosmic timescales, are interspersed with quiescent phases where the nucleus ceases to emit radiation. Fact 30. The immediate future of research involves multi-channel astronomy focused on strong gravity. New generation radio interferometers are designed not just for static shadow images, but for dynamic movies around Sagittarius A star, observing plasma spots moving in orbits over minutes and hours. Large optical telescopes equipped with adaptive optics will continue monitoring stars orbiting the galactic center, leading to more precise gravitational potential calculations. X-ray spectrometers utilizing microcalorimeters will deliver extremely sharp spectral lines and reverberation maps, enabling measurements of coronal height and wind dynamics. A space gravitational wave antenna operating at millihertz sensitivity will focus on pairs of intermediate and supermassive black holes, offering the potential for tomographic mapping of the universe of mergers. Broad sky surveys conducted in optical and infrared wavelengths will detect thousands of tidal disruption events, transforming infrequent occurrences into statistical data and establishing horizon physics as a field of accurate, reproducible measurements. 31st fact. During the years 2011 through 2014, in the surroundings of Sagittarius A star, a peculiar object named G2 served as bait. This object was a compact formation of dust and gas, following an extended orbit and reaching its pericenter at a distance measured in thousands of Schwarzschild radii. The astronomical community expected a significant display. The anticipation was that some of the substance would be dislodged, heated by tidal stresses, and emit X-ray and radio signals much like a small celebration for the black hole. Yet, the resulting surge was understated, as if the cloud had retained its integrity more effectively than a gaseous drop. This gave rise to a different possibility. G2 might not be solely gas, but a young star or a recently coalesced stellar pair cloaked in a dusty shell that endured the proximity. The progression of events demonstrated that even within the deprived galactic center, sustenance arrives in discrete amounts, and not every nearby transit culminates in a feast, with the interactions around the horizon being more intricate than simple frameworks suggest. Fact 32nd. Extremely unequal pairs, known as MRI, occur when a stellar mass object spirals towards a supermassive black hole over many years. The gravitational waves emitted by these systems are in the millihertz frequency band. These waves contain a fine map of Kerr geometry, encompassing hundreds of thousands of orbits, precessions, and resonances. It is projected that a next-generation space antenna will be capable of capturing these signals from faraway galaxies. This capability will enable testing the no-hair theorem for black holes. Even minor shifts in frequencies and phases will indicate deviations from the perfect metric. MRI form when, within the dense stellar environment of a galactic core, an object loses energy through gravitational interactions and plunges toward the center. The signals from MRI persist for a long time and yield accurate measurements of the central black hole's masses and spins. Furthermore, they offer clues about the composition of dense nuclear clusters which are dominated by massive stars, black holes, and intricate gravitational dynamics. The 33rd fact concerns microquasars, defined as nearby binary systems containing a black hole. These systems display jets that appear to move faster than light, despite the fact that light's speed limit, as established by Einstein, is not broken. The explanation lies in the geometry. The plasma moves at nearly the speed of light, directed at a slight angle relative to our line of sight. Because of this projection effect, the observed sideways speed surpasses the speed of light. Typical examples are sources such as GRS 1915 plus 105 and GRO J1655-40. Within these systems, the disk's brightness and spectrum, along with the X-ray corona and radio jet, vary in unison, akin to different acts of the same performance. During a flaring phase, the disk's thermal output rises, the corona diminishes, and the jet may break off and travel as discrete plasma blobs. Conversely, in the hard state, the jet remains steady and the X-rays are more energetic. These relationships establish a cosmic laboratory for understanding the interplay between the disk, corona, and jet. This model is applicable to objects with vastly different masses, as the fundamental principles governing microquasars also effectively explain the behavior of active galactic nuclei. Fact 34th. Black holes, in addition to narrow jets, also expel powerful winds. The spectra of active nuclei and X-ray binaries show blue-shifted lines of highly ionized iron, which are traces of ultra-fast outflows with velocities reaching tens of % of the speed of light. There are also warm absorbers and wide depressions in the ultraviolet, called BAL quasars, where winds carry away immense momentum. These flows are probably initiated by a combination of radiation pressure and magnetocentrifugal forces. They compete with accretion, transfer energy to the nuclear scale, and further into the interstellar environment. Observations of delays and polarization indicate that the geometry is complex. There are equatorial and polar components, variable funnels, and a dust screen. The result is significant for galaxy evolution. Winds and jets together regulate the thermostat, preventing gas from cooling uncontrollably and turning into stars. Fact number 35. Physicists create GRMHD simulations to comprehend the dynamics of a disk and jet near the horizon. This entails solving magnetohydrodynamic equations within the framework of curved spacetime and general relativity. The simulations produce turbulent vortices, magnetic loops, and hotspots, which are responsible for moving angular momentum away and directing energy towards the corona and jets. Subsequently, radiation transfer is incorporated. Rays are followed along geodesic paths considering redshift, Doppler shifts, and gravitational focusing. This leads to the generation of synthetic snapshots and light curves that can be matched with observations from radio interferometry and X-ray instruments. This methodology is employed to validate theories concerning disks that are magnetically arrested, the altitude of the corona, and the configuration of magnetic fields around M87+ and SGRA. When models and observational data align, it signifies more than just an attractive visual. It confirms that the initial equations, the plasma's microphysical properties, and the selected metric correctly represent the actual conditions at the event horizon. The 36th fact.
Stellar-borne black hole masses are not uniformly spread. Theoretical models have long indicated a pair instability gap. Within the cores of supermassive stars, at temperatures near 1 billion Kelvin, gamma quanta generate electron-positron pairs. This reduces pressure, causing the core to collapse in an explosion. Should a helium core possess substantial mass, a star might survive multiple pulsations, shedding its envelopes, pulsational pair instability, resulting in a comparatively light black hole. For even larger masses, total pair instability ensues, completely annihilating the star without any remnants. In this mass range for black holes formed by solitary stars, an absence of objects was anticipated. Gravitational wave observations have introduced further complexity. Systems with components appearing to be in the forbidden zone are sometimes detected, pointing towards hierarchical mergers or peculiar low metallicity environments. Ultimately, the mass distribution serves as a record of stellar evolution and their pairings in dense clusters. Fact 37th. Millions of stellar mass black holes are thought to exist in our galaxy, found both in binary systems and as isolated objects. Precise estimations differ, but figures in the tens of millions are discussed, scattered throughout the galactic disk and bulge. What we observe is merely a fraction, a few dozen to 100 X-ray binaries, where accretion makes the invisible object detectable. The others are undetectable. Their presence is revealed by microlensing, which is a temporary amplification of a distant star's light when an unseen mass moves across the line of sight. For these events, the typical duration extends from weeks to months. Occasionally, a minute astrometric displacement of the star's position can be noted, allowing the mass of the lens to be calculated. This results in a dark object with solar masses and no intrinsic light. Extensive surveys and accurate astrometry are progressively opening up a catalog of these silent gravitational apparitions, providing data to estimate their population, speed distributions, and even to glimpse the kicks they received at birth from supernovae. The 38th fact. Superradiance is an unusual way to extract energy from a spinning black hole. The Zeldovich relativistic effect is a well-known instance. A wave bouncing off a rotating object can be amplified by its spin. In astrophysics, applying this directly is difficult. Yet, if light bosons, like axion-like particles, are present, they can create atom-like levels near a black hole. Via superradiance, these levels get pumped up, much like a laser medium. The result is a puffed-up, cloudy structure that steals angular momentum from the black hole, slowing it down, and can radiate narrow gravitational waves for years. Analyzing the spin distribution of stellar and supermassive black holes already imposes limits on the potential masses of these particles. If their masses were in specific ranges, there would be fewer fast-rotating black holes. This shows how horizons become testing grounds for physics outside the standard model. Fact 39th. Active nuclei that change before our eyes are a phenomenon where a quasar loses or acquires broad lines in its spectrum over the course of years and significantly alters its luminosity. The standard unification model attributed differences to viewing angle. But in these instances, the object itself is changing. Observations revealed that dust geometry is sometimes the cause. A cloud of dust blocks the central light source. Yet in several cases, the crucial factor is accretion starvation or a sudden increase. The rate at which material arrives decreases. The thin disk shifts to a hot, sparse regime, and the photons that ionize the broad line region vanish. Subsequently, the process occurs in the opposite direction. By measuring the time lags of gas line responses to continuum fluctuations, scientists determine the dimensions and structure of these regions, and by their speeds and colors, the physics governing the transitions between states, which draws parallels between galactic nuclei and microquasars. These transformers provide a unique chance to examine the reconfiguration of the entire system from the event horizon to areas spanning hundreds of light years. The 40th fact. Sagittarius A star, the nearest supermassive black hole, has served as a proving ground for testing general relativity in a strong field within human observable timeframes. The star S2, which completes an elliptical orbit in under 20 years, reaches speeds of several thousand kilometers per second at its closest point and approaches distances where relativistic adjustments become apparent. During its periseer passage, a gravitational redshift of its spectral lines was observed. Years later, preliminary indications of relativistic pericenter precession emerged, meaning the orbit's ellipse turns by a small yet measurable angle with each revolution. Taken together, these phenomena are consistent with the predictions of the Kerr metric for the relatively quiescent black hole at the center of the Milky Way. The next steps involve observing even closer stars and hot gas clouds, whose swift orbital movements will enable the tracking of space-time history on a minute-by-minute basis, verifying the geometry near the event horizon with unparalleled precision. Fact 41. According to classical general relativity, the area of a black hole's event horizon cannot shrink. This principle is known as the second law of black hole mechanics, established by Hawking and Bekenstein. When two objects merge, the total area of their horizons is expected to grow. Gravitational waves carry energy away, but they prevent any violation of the horizon's entropy conservation. This assertion can be tested. By analyzing the initial part of a gravitational wave signal, the masses and spins of the merging pair are determined, and their respective horizon areas are calculated. Subsequently, the characteristics of the resulting black hole and its area are determined from the ringdown that occurs after the merger. The initial observed events, such as the significant GW1509 signal, indicated consistency with this law within measurement uncertainties, showing an increase in area. This serves as a test for both geometry and thermodynamics under strong field conditions, essentially a cosmic analog of the second law. Furthermore, if a singularity were to exist without an event horizon, this law would be broken. Therefore, such tests indirectly support the cosmic censorship hypothesis, which posits that singularities are always concealed behind event horizons. Fact 42. The internal structure of a rotating black hole, as described by Kerr's solution, is complex. In addition to the outer horizon, there exists an inner horizon, known as the Cauchy horizon. Within an idealized mathematical model, space-time extends beyond this horizon, giving rise to exotic areas where causality is altered. Physics, however, points to instability. Even minor perturbations, like incoming dust or light, are magnified, causing the energy at the inner horizon to formally increase, a process called mass inflation. It is probable that a real black hole does not possess a seamless extension. The inner horizon evolves into an area characterized by a cascading breakdown of curvature. Crucially, all these phenomena are concealed from external observation. No signal originating from inside can breach the outer horizon, rendering the described effects strictly theoretical. Despite this, their importance is undeniable. The stability of the Cauchy horizon impacts the theory's predictability, global hyperbolicity, and debates concerning firewalls, quantum adjustments, and holography frequently center on these internal frontiers. Fact 43. Stellar dynamics around a supermassive black hole are controlled by the lost cone, an area of angular momenta where an orbit will guide an object either within the tidal disruption radius or to the event horizon. Two-body and resonant relaxation progressively feed stars into this cone, and infrequent casualties serve as fuel for tidal outbursts. The Hills mechanism is a distinct subject.
When a close binary star plunges into the core, tidal forces rip the pair apart. The black hole captures one component into a narrow orbit, and the other is flung out as a hypervelocity star, with speeds reaching thousands of kilometers per second. These fugitives have been identified in the Milky Way's halo, and their paths indicate the direction of the galaxy's center. The S-star family also exists there, young, swift on eccentric orbits, probably formed in the disk or transported by dynamic processes. Collectively, these events narrate the story of gravity's stealthy pursuit near the central behemoth. Fact number 44. What is the origin of black hole pairs detected by instruments? Several pathways exist. One involves the isolated evolution of a massive binary star which moves closer as it goes through a common envelope. Low metallicity decreases stellar winds, resulting in more massive cores and potentially aligned spins. This leads to mergers with generally consistent rotation directions. A different mechanism is dynamic. Within globular and nuclear star clusters, gravitational interactions pair up individual stars, expelling less massive ones. In these cases, spins are frequently random, and hierarchical mergers can occur, creating components with masses outside the typical range for single stars. A third possibility involves disks around active galactic nuclei. Here, gas migration, pressure traps, orbital alignment within the disk, and mass increase via accretion are factors. Observational data, such as the spread of eccentricities, masses, redshifts, and crucially, the angles between spins and orbits, allow statistical differentiation of each scenario's contribution over time. Fact 45. Explaining quasars in the early universe requires seeds of supermassive black holes that had time to grow in a few 100 million years. One scenario involves direct collapse. In halos with atomic cooling temperatures where molecular hydrogen formation is suppressed, e.g. by a strong Lyman-Werner background, gas doesn't fragment into stars but falls as a single mass, creating a supermassive star of 10,000 to 100,000 solar masses, and subsequently a quasi-star with a black core. Another possibility involves the remnants of the first stars, population 3, with masses of several hundred suns, which, under suitable conditions, grow in a super-Eddington manner and via mergers. A further path exists through a series of collisions in very dense young clusters, accumulating intermediate masses. Investigations are proceeding on multiple fronts: the luminosity and spectral lines of the most distant quasars, their population statistics, evidence of active nuclei in galaxies at high redshifts, and indirect signs of feedback influencing the ionization and metallization of the early intergalactic medium. Fact 46. M87 and Sagittarius A star, the two black holes that generate the most discussion, look alike in their shadows but operate on different timelines. The typical gravity time, Tg, equals gm over c cubed for SGR A star is around 20 seconds, with an orbit on its inner stable circle taking tens of Tg, or minutes. For M87, Tg is measured in hours, and a full rotation takes weeks. This means that extended interferometric observations of the event horizon averages out the activity around M87, but smooth over the swift changes occurring at SGRA, as hotspots and streams can shift configuration within the observation period. Interstellar scattering adds another challenge when studying the galactic center. Electrons in the line of sight distort the radio picture, requiring compensation. To preserve contrast, closure phases and polarization are utilized. These methods have shown that the magnetic fields of both objects are organized and their accretion flow is spinning. However, at SGRA, photons change their state more quickly than we can record their movement. The 47th fact. Quasi-periodic eruptions in soft X-rays have been observed in some galactic nuclei that appear tranquil. These outbursts recur over periods of hours or days, intensify in minutes, and diminish just as rapidly, boosting luminosity by several to tens of times. Radio counterparts are typically faint, indicating the jet plays a minor part, with the inner disk and corona being the main drivers. The central black hole masses in these systems are estimated at 10 to the 5th to 10 to the 6th solar masses, yielding characteristic light scales that match observed time lags. Interpretations are debated. Partial tidal disruption of a star in an eccentric orbit, localized thermal instabilities in the disk, or periodic gas accretion from a wind. The period's initial stability is striking, but it then starts to drift as if the orbit or accretion rate is gradually altering. While consensus is lacking, QPEs have become a novel means to study the physics of thin accretion layers around low-mass supermassive black holes. The 48th fact states that X-ray reverberation, observed as echoes lasting from seconds to hours between the corona and the disk, serves as a ruler for measuring the geometry of the near-horizon zone. In a lamppost picture, a compact corona positioned over a pole emits light downwards. A portion of these photons bounce off the disk, generating an iron line and a hump at energies of tens of keV. Variations in the initial continuum are detected first, with the reflected signals arriving later, with a time delay of approximately a few GMC cubed, meaning milliseconds in microquasars and minutes to hours in active galactic nuclei. These delays, combined with the shape of the lines, enable the assessment of the corona's height, frequently below 10 gravitational radii, the disk's ionization level, and even highlight the bending of light predicted by general relativity. By scaling these lags with mass, an independent measurement of the black hole's mass is obtained, adding to the traditional optical Rever mapping of broadlines. The outcome is a rare phenomenon, almost geodesic tomography of spacetime, achieved through light delays. The 49th fact highlights that a progenitor star's metallicity strongly affects the black hole's mass. Stars with fewer heavy elements exhibit less powerful, linearly driven winds, leading to reduced mass loss before collapse. This results in more massive cores and, consequently, more massive black holes. In tight, fast-spinning binary systems, chemically homogeneous evolution can occur. This happens because mixing stops the star from swelling, prevents it from entering destructive phases, and keeps the pair close, setting the stage for two massive black holes to merge later. Including a fallback during a supernova creates gentle birth kicks, improving the system's survival odds. Gravitational wave data suggests that heavier events are more common at higher redshifts, where the average metallicity is lower. This fits the idea of the early universe being depleted of heavy elements. Yet, direct proof of cause and effect is lacking, so scientists are careful with their conclusions, combining models of stars, binary system behavior, and what is observed. 50th fact. Dual supermassive black holes are anticipated results of galaxy mergers, yet detecting them at sub-parsec scales is challenging. At kiloparsec separations, two active nuclei are directly visible. At closer ranges, indirect signs are pursued. Quasar light variability, paired or shifting peaks in broad spectral lines, and S-shaped jet deflections. Numerous such indicators have proven to be rare noise, cloud dynamics, or disk phenomena, causing the scientific community to adopt a rigorous stance on potential candidates. For a long time, theoretical discussions revolved around the final parsec problem. How would a binary pair dissipate orbital momentum once the nearby stars have been effectively cleared out? Proposed explanations involve three-dimensional, rather than spherical, gravity, gas disks capable of transferring angular momentum, and the presence of massive perturbing bodies. The nanohertz gravitational wave background, identified through pulsar timing analysis, is precisely what is expected from an ensemble of such binary systems.
This background will not identify a specific offender, but will validate that over billions of years, the universe has hosted a multitude of slow, intimate interactions among massive black holes.
Fact 51. X-ray polarimetry has emerged as a new method for probing the geometry of areas near the event horizon. If spectra and delays indicate what and when, then the polarization vector's orientation shows where and how fields and rays are oriented. Contemporary instruments have achieved the first measurements of polarization fraction and angle in black hole binaries and active galactic nuclei. Moderate yet consistent polarization is observed in the hard state. Upon shifting to the soft state, the angle alters, suggesting the corona's proximity to the disk or its extension into a jet space. The reflected component, linked to the iron line, exhibits distinct polarization, enabling the separation of coronal and disk contributions based on their characteristic signals. By matching polarization phase rotations with quasi-periodic oscillations, scientists are able to reconstruct the photon source's altitude and the extent of trajectory bending predicted by general relativity. This represents an uncommon situation where a single light curve yields a three-dimensional visualization of phenomena not directly visible. 52nd fact. The dream test for general relativity involves a pulsar orbiting closely around Sagittarius A star. Its pulses act like precise atomic clock signals, responsive to time dilation, precession, and the Shapiro effect. However, radio waves at the galaxy's core scatter within turbulent plasma, smudging their fast pulse rate. In 2013, a magnetar, a scarce pulsar relative, was discovered near SGR-A. Its signals aided in quantifying the scattering level and the magnetic conditions along our view. It was found that the plasma haze was less dense than anticipated, thus preserving the possibility of detecting ordinary pulsars. Should a millisecond pulsar be detected, functioning as a synchronized beacon on an orbit lasting months to years, its timing data will provide mass measurements of exceptional accuracy, along with spin and even the central object's quadrupole moment. This would offer a direct verification of the Kerr metric's hairless property. Currently, this objective necessitates extensive surveys on frequencies with reduced scattering and considerable patience. The pursuit resembles fishing in a turbulent river, yet the potential reward justifies the endeavor. 53rd fact. Black holes and dark matter are theorized to exist at the event horizon and within galactic centers. Should a supermassive black hole have formed gradually within an established halo, calculations suggest a spike, a dense region of dark matter nearby, potentially boosting signals from annihilation. In actual galaxies, features like stellar bars, tidal effects, and mergers can obscure this predicted profile, leading to a lack of direct evidence. Gamma-ray data from the Milky Way's core offers mixed indications and sets firm constraints. Alternatively, dark matter might impact black hole growth by feeding extra mass to the nucleus and changing star cluster dynamics, a subtle model-dependent influence. It is accurate to state that the interaction between black holes and dark matter is a dynamic field. Observational data is refining the range of possibilities, but a complete understanding is still pending. Any assertions about detecting these spikes warrant careful consideration and cross-validation using various telescopes and approaches. Fact 54 states that flares in black hole binary systems create a distinctive hysteresis loop on the hardness-intensity diagram. The process begins with the object in a quiet state, increasing its brightness in the hard spectrum, characterized by a hot corona and a steady, compact jet. After reaching a certain threshold, the system shifts to a soft state. The thin disk becomes incandescent, the hard spectral component diminishes, the jet fades, and occasionally individual plasma pellets are shot out. As brightness decreases, the return transition happens at a different luminosity level, resulting in the loop, which signifies asymmetrical physics. The reasons are thought to be the evaporation and condensation of the inner disk, alterations in the corona's height, and magnetic flux. This cycle spans weeks to months, but applies to larger scales. In active galactic nuclei, comparable transitions extend over years to decades and account for the observed phase changes of quasars. Hysteresis here serves not merely as an aesthetic pattern, but as a guide to modes, connecting the disk, corona, and jet as a unified operational system. Fact 55th. Water can serve as a laser for astrophysicists. In the centers of certain galaxies, H2O molecules within the dense, warm disk layers generate a megamaser, which is intense microwave radiation at 22 gigahertz. In NGC 4258, these lamps are arranged along a nearly perfect Keplerian disk. This arrangement enabled the measurement of the central black hole's mass and the geometric distance with reference accuracy. Velocity was determined by frequency shift, radii by angular position, and accelerations by changes in these. The outcome is straightforward Newtonian mechanics close to the event horizon, without requiring complicated assumptions about luminosity. Systems like these are uncommon but extremely valuable. They are used to calibrate the universe's distance scale, refine the Hubble constant, and offer a method for weighing intermediate mass black holes. In situations where dust renders optical methods ineffective, radiomasers create a disk map with precision down to billionths of a second, illustrating gas circulation within the final tens of thousands of gravitational radii before the inescapable boundary. The 56th fact. Radio galaxies exhibiting an X-shaped morphology serve as visual diaries of sharp turns in jet trajectories. The images reveal two pairs of lobes. One is active and narrow, penetrating the intergalactic gas, while the other consists of faint wings extended perpendicularly. The spectral age of these wings is typically greater, meaning their electrons have aged. This implies that the outflow previously followed that path, but the axis subsequently realigned. Several mechanisms are proposed. A fast flip of the supermassive black hole spin occurring after a merger with another black hole can lead to nearly immediate changes in jet direction. A slower mechanism involves the alignment of the inner disk with the spin plane, as described by Bardeen-Pedersen. The jet axis drifts, leaving arc-shaped traces. Another hypothesis is backflow, where plasma from the main lobes returns and spreads out laterally. Low-frequency surveys, such as those conducted by LOFAR, are discovering an increasing number of these relics. By analyzing their symmetry and cooling times, scientists can estimate over how many millions of years the nucleus underwent such switching, offering glimpses into the history of mergers and directional shifts of the central monster. Fact 57. Narrow-line Seyfert 1 galaxies, NLS-1, are compact counterparts to quasars. These objects feature black holes with masses ranging from millions to tens of millions of solar masses, and they exhibit a high proportion of Eddington luminosity. Their spectral characteristics include an abundance of Fe2, a narrow H-beta line, and a frequent soft excess in their X-ray emissions. It was long thought that powerful relativistic jets were exclusive to massive galactic nuclei. However, the deployment of gamma-ray observatories revealed jetted NLS-1. A subset of these galaxies displays variability and high-energy outbursts similar to mini-blazars. This suggests that the accretion disk can evolve into a slim state when accretion rates exceed the Eddington limit. In this state, radiation becomes partially trapped and is expelled by the outflow, and magnetic fields can assemble a jet even when the black hole mass is relatively low. It is important to note that mass estimations derived from line widths in these objects might be underestimated due to geometrical effects and radiation pressure. Nevertheless, the overarching conclusion is that jet launching mechanisms are activated across a broader spectrum of conditions than previously proposed by earlier unification models. Fact 58. Black holes are leading the way in multi-wavelength astronomy and neutrino physics. When a blazar, a jet pointed nearly at us, flashes, high-energy neutrinos, along with photons, can originate in its depths. In a notable instance, a high-energy neutrino detected by an Antarctic instrument matched an active blazar in both sky position and timing, while ground telescopes detected a related gamma-ray burst. This explanation favors hadronic models, suggesting protons in the jet interact with photons, creating pions that decay into neutrinos and gamma rays. However, the current statistics are marginal, and some associations are not confirmed due to high background noise and random fluctuations. Despite this, the potential connection establishes black holes as sources of cosmic rays at peta-electron-volt energies and higher. Radio galaxies, such as the close Centaurus A, and blazars with strong jets are primary candidates, and every multiband burst serves to evaluate models of particle acceleration at the event horizon and within jets. 59th fact. Polarization in the submillimeter and millimeter bands has become a compass for magnetic field maps near the horizon. Interferometry of M87 star showed not just a shadow, but a map of polarization vectors. They are aligned like hoops and spokes, hinting at a strong toroidal field supporting the jet's base. For Sagittarius A star, the measured Faraday rotation measure, the plasma's rotation of the polarization plane, is huge, indicating a hot, ionized environment around the hole and limiting the accretion rate from above. If too much gas were falling, depolarization would consume the signal. By range of estimates, the typical accretion rate into the galactic center is very modest today, orders of magnitude less than solar mass per million years, which explains its hungry mode and rare outbursts. Aligning polarization maps with GRMHD models reinforces the finding. Magnetic flux at the horizon is large, and disks often operate in a magnetically arrested mode, where the jet is fueled by the black hole's own rotational energy. Fact 60. Searches for binary supermassive black holes frequently depend on periodicity in quasar light, but nature is deceptive. Accretion, red noise, can readily be mistaken for cycles. However, a few systems capture interest. In one instance, the optical light curve displayed an almost sinusoidal shape for years, with a period spanning several years, suggesting the pair's orbit was modulating Doppler boosting. Another case involves a well-known blazar with a historical record of outbursts spanning a century, which shows quasi-periodic double peaks. These are interpreted as the secondary companion striking the primary's accretion disk when passing pericenter on a significantly inclined orbit. Spectroscopic data occasionally show bifurcated broad line peaks, indicating two moving sources, and radio jets on parsec scales curve in an S-shape, implying axis precession. While each of these indicators individually lacks certainty, when combined with the nanohertz gravitational wave background, they form a coherent view. Binary nuclei are present, but capturing them directly before their ultimate coalescence proves challenging. The 61st fact states that the Eddington limit acts as a light ceiling for accretion. This occurs when the pressure from radiation, which scatters off electrons, counteracts gravitational pull, halting the free fall of gas. The formula provides an approximate characteristic luminosity of L-ed approximately 1.3 times 10 to 38 m by mo erg per second for plasma undergoing Thomson scattering. However, natural processes can bypass this limit. One way is through beaming, where radiation is emitted directionally within a narrow cone. This allows the local flux to surpass the average limit without causing the disk to destabilize. Another mechanism, active at high accretion rates, is the slim disk scenario. Here, a photon trap and advection efficiently move energy inward before it can escape, while the disk's geometrically thicker structure provides self-shielding. Consequently, super-Eddington events are observed in reality. It is estimated that ultraluminous X-ray sources and certain Seyfert galaxies operate in this manner, expelling surplus momentum via winds. Thus, the Eddington limit serves as a reference point rather than an absolute barrier, as it can be overcome through adjustments in geometry, energy transport, and the magnetic configuration of the flow. Fact number 62. When black holes merge, they leave behind in spacetime not just a chirp and fading overtones, but also a subtle, constant imprint known as gravitational memory. As the waves dissipate momentum, observers far away observe a single jump in the metric. Two test masses, previously oscillating together, end up slightly shifted after the wave front has passed. This effect has both linear and nonlinear Christodoulou memory parts. Both are very small for single events detected by LIGO. However, the combined effect from billions of faraway mergers creates a slow, creeping shift that millisecond pulsar timing is highly sensitive to. Pulsar timing is actively searching for these correlated skywide trends. For detectors on Earth, gravitational memory is a significant hurdle. It necessitates either infrequent, extremely powerful and nearby events, or sophisticated analysis of numerous signals to detect the faint, step-like tail that follows the newly formed holes ringing. Fact 63. The magnetosphere of a black hole is not a void, but a spinning electromagnetic engine. High spin and the warping of spacetime create electric fields. Even a small amount of plasma is enough to complete electrical circuits and reach a state that is almost without inertia, force-free. The question arises about the source of this plasma, given that the horizon itself is cold. It is produced by cascades of electron-positron pairs. Gamma rays resulting from particle acceleration due to curvature, along with photon-photon interactions involving the disk's ultraviolet and X-ray emissions, generate these pairs. This process fills in the gaps, areas where the magnetic field is not shielded quickly enough. Inside the magnetosphere, there are light surfaces where co-rotation would equal the speed of light. Open magnetic field lines exit through these surfaces, pulling out a relativistic flow, which forms the foundation of a jet. Currents are completed via the disk and corona, leading to immense potential differences. The Blandford-Znayak mechanism taps into the rotational energy, transforming the black hole into a cosmic generator that fuels the jet and wins. The 64th fact states that radio galaxies are classified into two Fonarov-Riley families. FR1 type are designated edge-dark. Their jets lose focus as they travel, dispersing into clumps and cocoons, and their brightness diminishes toward the extremities. This is usually associated with moderate power levels and a denser surrounding medium, where the flow captures ambient gas and decelerates. FR2 type are termed edge-bright. They feature narrow, straight jets that strike intergalactic gas, creating hotspots at the lobe extremities. These galaxies possess higher power and propagate through a less dense medium. The boundary between these types is not precise and can vary with mass and environment, but it signifies distinct physical processes, differing modes of supply and magnetic flux at the horizon, variations in ambient density, and the rate of matter entrainment. In the spectra of their nuclei, this manifests as LRG/HRG, low and high excitation radio galaxies, akin to the hard and soft states of microquasars. Consequently, a scalable model emerges. The identical disk-corona jet engine operates across megaparsec scales, influenced by the varying aerodynamics of the environment. The 65th fact. Should the Sun be miraculously swapped for a black hole of identical mass, the planets would not be pulled into the void. Their orbits and periods of revolution would stay the same, as gravity at a distance is consistent. However, all other aspects would be altered. In over 8 minutes, Earth would be plunged into darkness, photosynthesis would cease, and the climate would start to chill considerably. Over days to weeks, the average temperature would fall well below freezing.
oceans would begin to ice over from their surface. But the warmer deep layers and geothermal heat flow, some 0.1 watts per meter squared, would sustain liquid water beneath the icy crust for an extended period. Volcanic activity and tidal warming, which is minimal for us, would serve as localized havens. The solar wind would vanish, reshaping space weather, and the frequency of auroras would decrease. There would be no suction effect, nor an immediate breakdown of celestial mechanics. The primary light source in the sky would simply extinguish, leaving an unseen, relatively tranquil object at the solar system's core, which, under normal circumstances, gains virtually no material for accretion and thus emits no light. Fact 66. The galactic center preserves evidence of recent Sagittarius A-star outbursts as light echoes on molecular clouds. Some 10 to 100 years ago, the supermassive black hole was more intensely fed with gas. Its intense radiation impacted nearby clouds, causing iron to emit a fluorescent line around 6.4 keV. Currently, with the flare long gone, we see the illumination appearing to move across the cloud. Bright patches emerge and fade over the years, akin to a spotlight moving along a rough surface. This displacement is not attributable to the cloud's internal processes. It is a reflection of the core's transient past activity. The speed and magnitude of these echoes allow for an assessment of the former flare's intensity and the cloud's exact position within the center's three-dimensional map. This effectively forms a timeline. SGR-A is currently quiescent, but about 100 years ago, it probably briefly ignited like a mini-active nucleus. Fact 67. The Nobel Prize in Physics in 2020 was divided between the theory and observations of black holes. Roger Penrose was honored for a rigorous proof that black hole formation is an unavoidable outcome of general relativity under generally common collapse conditions. Reinhard Genzel and Andrea Ghez received the prize for discovering a supermassive compact object located at the center of the Milky Way. For decades, their groups monitored the orbits of S-family stars near Sagittarius A-star, measuring their accelerations, pericenters, and precession with unimaginable accuracy. The physical core of their result is that the observed mass is concentrated within a volume where nothing stable except a black hole can be accommodated. This connection between mathematical formulas and celestial observations demonstrated how Penrose's precise mathematics and the fragile diffraction spots from telescopes combine into a single depiction of the gravitational abyss residing in the core of our galaxy. The 68th fact. The most unassuming galaxies can also harbor black holes. Dwarf systems contain active nuclei with masses estimated at hundreds of thousands of suns or less. Galaxies lacking a prominent bulge, yet showing central variability and narrow lines, serve as an example. Occasionally, water megamasers are detected, pointing to a compact Keplerian disk. These micronuclei are significant as living clues to the genesis of supermassive behemoths. The presence of small holes in dwarfs suggests that their origins might have been abundant and widespread in the early universe. Another category comprises rogue black holes, which are the remnants of disrupted satellite galaxies or the result of gravitational kicks that propelled them from galactic centers. They now drift through halos, sometimes flaring up as minor, misplaced active nodes. The search for these wanderers focuses on displaced nuclei, line asymmetries, and X-ray sources located away from stellar cores. Fact 69th. Ultraluminous X-ray sources are objects located outside galactic centers, with luminosity surpassing the Eddington limit for an ordinary star. For a considerable period, they were almost certainly identified as intermediate-mass black holes. However, following years of observation, a portion of ULXs have shown a pulsar nature. Their light revealed consistent pulsations, which is a characteristic sign of a rotating, magnetized neutron star core. This indicates that fluxes exceeding the Eddington limit are not exclusive to black holes.
Geometric focusing of radiation, magnetic channels, and photon traps enable neutron stars to significantly surpass the traditional limit. While this doesn't rule out the existence of intermediate black hole candidates, it necessitates a cautious approach. High luminosity alone is not definitive proof of mass. Proper identification relies on spectral data, pulsation detection, cyclopic lines, and the dynamics of optical donors. A comprehensive set of indicators to differentiate a powerful accretion phase from objects with substantial gravity. Fact 70. The demography of compact objects involves discussions of mass gaps. The lower one is between the heaviest neutron stars and the lightest black holes. For an extended period, X-ray binaries did not reveal black holes weighing less than approximately 5 solar masses, suggesting the existence of a forbidden zone. Gravitational wave detections have introduced new perspectives. In one observed event, the secondary object was found to be in the mass range of roughly 2 to 3 solar masses, raising the question of whether it was an exceptionally massive neutron star or a surprisingly light black hole. The upper gap is associated with the pair instability evolution of supermassive stars. While isolated progenitor stars do not produce black holes within a certain mass spectrum, hierarchical mergers occurring within clusters can precisely adjust masses into this forbidden corridor. Consequently, these gaps are not absolute barriers, but rather weak points within an intricate web of formation pathways, where the statistics and physics of stars are intertwined with the dynamics of close interactions. Fact 71. Hawking's concepts regarding quantum evaporation are verified in laboratory settings not using genuine gravitational holes, but rather their counterparts, which are artificial horizons. Within superfluid Bose-Einstein condensates, an area is established from which sound is unable to move upstream. Optical waveguides and photonic crystals are used to model a traveling boundary of the refractive index, serving as a horizon for light. These systems exhibit correlated pairs of quasiparticles, either acoustic or optical, on either side of the boundary, aligning with the predicted pair generation mechanism at the horizon. While these Hawking sparks effectively illustrate the underlying principle, they do not confirm the evaporation of astrophysical black holes. The difference lies in the forces at play. Gravity and space-time distortion are involved in astrophysical black holes, whereas an effective medium with an analogous metric is at work in these experiments. It is crucial to differentiate. The experiments lend support to the overarching concept of quantum pair production at a horizon, but applying these findings directly to celestial masses requires careful consideration. Fact 72. When discussing the nature of compact dark objects, alternative possibilities to the Kerr black hole concept include boson stars, gravastars, configurations featuring exotic fields, or even wormholes. A shared characteristic among these is the lack of a genuine event horizon. Consequently, light and gravitational waves could be partially reflected, generating an echo subsequent to the primary merger signal. The visual representation of the shadow would display modified borders and contrast, and its spectral analysis would reveal altered reflection line structures. Based on interferometry measurements of the shadows of M87 star and SGRA, and calculations of the gravitational wave ring-down bell, the standard Kerr metric remains a good descriptor of current observations. Nevertheless, opportunities for exotic explanations persist because the signals are faint, measurement systematics are substantial, and alternative models offer adaptability. The accurate statement is, currently, there are no confirmed deviations from the Kerr model, but the pursuit of echoes and fine-grained effects persists, as these are the very features that would differentiate a horizon from a reflective skin. The 73rd fact states that hotspots occasionally appear in the near-infrared emission of Sagittarius A star. These are compact plasma accumulations heated within the corona situated above the accretion disk. Using long baseline interferometry, it was observed that one of these spots completed several orbits around the black hole over a duration of approximately tens of minutes. Concurrently, the polarization vector of the light smoothly changed its orientation, giving the impression of observing an orbit within a strong field accompanied by rotating magnetic field lines. The observed period and amplitude are consistent with movement at radii of only a few gravitational radii. At these close distances, relativistic effects such as Doppler boosting, apparition, and gravitational redshift are predominant. Although these flares are minor in energy and dissipate rapidly, they are extremely valuable, serving as a precise timer near the event horizon. By analyzing their periodicity and polarization shifts, one can determine the black hole's spin, the disk's inclination, and the magnetic field's configuration without needing to wait for infrequent, significant accretion events. Fact 74th. The M87 jet serves as a model for understanding the aerodynamics of relativistic plasma. At scales ranging from tens to hundreds of thousands of gravitational radii, its cross-sectional profile approximates a parabolic curve with a gradual expansion. This suggests magnetic collimation and the influence of external pressure from the surrounding medium. Beyond this region, the jet takes on a more conical shape due to decreasing pressure and inertial flow. The images show edge brightening, characterized by bright borders, which imply a speed difference between the fast inner core and the slower outer shell. This phenomenon helps preserve collimation and accelerate particles. The polarization and brightness observed at the base of the jet are consistent with a magnetically arrested disk model, where significant magnetic flux is channeled towards the event horizon, and the black hole's rotational energy is extracted via electromagnetic processes. Encountered along its path, shock structures known as recollimation shocks cause localized flares and organize the jet structure over parsec scales, demonstrating how microscopic physics near the event horizon scales up to form immense cosmic formations. The 75th fact. Future ground-based gravitational wave detectors, equipped with kilometer to tens of kilometers long arms, are designed for black hole spectroscopy. Their increased sensitivity will permit not only the reliable capture of the main ring-down signal post-merger, but also the detection of distinct overtones. This capability will allow for simultaneous verification of no-hair properties through multiple notes. In cosmology, this signifies the creation of a merger map extending to high redshifts and direct standard siren distance determinations. For astrophysics, it promises a statistical analysis of spins and masses encompassing intermediate black holes formed within dense clusters. Simultaneously, a space-based millihertz antenna will pick up the in-spiral of heavy pairs years before their merger, and pulsar timing will refine the background originating from supermassive nuclei. While direct black hole mergers are electromagnetically silent, hints might appear as flares from perturbed gas within active galactic nuclei disks. Collaborative observations will provide a unique chance to integrate event horizon geometry, plasma, and galaxy evolution into a single, verifiable story. Fact 76th. Initially, the cooling flow problem in galaxy clusters suggested abundant star formation. It was thought that the hot intergalactic gas in the centers of these clusters would quickly cool and accumulate in their cores. However, observations indicated otherwise. Star formation was limited and the gas stayed hot. It was found that supermassive black holes function as thermostats. Their jets create voids, termed bubbles or cavitations, within the gas that emits X-rays. The enthalpy of these bubbles, approximately 4 PV, offsets energy lost through radiation. These bubbles ascend, carrying cold gas filaments with them and stirring the surrounding medium. Along their ascent, faint shock fronts and sound waves, similar to those observed in the Perseus cluster, are detectable. This process completes a cycle. When the central gas cools excessively, droplets form, chaotic cold accretion, and descend towards the black hole.
This, in turn, enhances its accretion and heating. Consequently, over timescales of tens of millions of years, a feedback loop operates, providing steady but not excessive heating, which prevents intense star formation in galaxy clusters. Fact 77. Variability is characteristic of accretion, and this trait scales for black holes. Their X-ray brightness curves are similar to red noise. Fluctuation power increases with longer time periods, but is interrupted at a specific frequency. This break frequency consistently changes with mass and accretion rate, creating a variability plane with these factors. Smaller, less massive objects blink faster, while larger, more massive ones blink slower. Another indicator is the RMS flux connection. The brighter the system is at any given time, the greater the relative fluctuations, as if variations are amplified as they move inward. The rolling disturbances model explains this. Inconsistencies in viscosity and material flow begin at greater distances and, moving inward, influence the light from the corona and disk. Optical and ultraviolet observations frequently show delays following X-rays, indicating the outer layer's reaction to heat. Occasionally, a slow optical pulse precedes, suggesting the disturbance originated from deeper within the disk. The 78th fact. Black hole flares are a result of the thermal viscous instability within the disk. When cold, hydrogen in the disk is mostly neutral, leading to low opacity and mass accumulation. If a ring's temperature hits the partial ionization threshold, opacity spikes, intensifying heating. This engages the upper branch of the S-curve for equilibria. A heating wave travels across the disk, shifting it to a hot, luminous state for weeks to months. Subsequently, as fuel runs out and cooling sets in, a backward wave dims the light. X-ray exposure of outer layers alters thresholds and lengthens the plateau phase. In periods of profound quiet, the inner disk might vaporize into a hot, thin outflow similar to an ADAF, and radio jets emerge during these transitions. This same physics, extended over years, is considered for active galactic nuclei as a cause of variability. The disk builds up material over extended periods, then rapidly expends it, with the corona and winds adding their part to the shifting harmonies. Fact 79th. The cosmic X-ray background, appearing as a dim veil across the sky with a peak intensity around tens of keV, has been identified as the combined emission from billions of active nuclei, including those that are hidden. To construct its spectrum, sources with strong absorption and significant Compton thickness, featuring NH columns exceeding approximately 10 to the 24th power per square centimeter, are required. Their direct light is absorbed, but reflected and leaked photons gather energy in the high energy range. Synthetic background models are built by combining quasar luminosity functions, absorption distributions, and their changes with redshift, aiming for consistency with the spectrum and the count of detected sources. Extensive surveys conducted by Chandra and XMM have resolved a substantial portion of the background at low energies, while the NuSTAR telescope has revealed a population of hidden nuclei in the hard keV range. Using the Sultan argument, the active galactic nuclei luminosity integral is correlated with the total black hole mass at present, resulting in an average radiative efficiency of tenths, suggesting considerable spins in a significant number of central supermassive objects. Fact 80. The merging black hole signal encodes physics through its frequency and amplitude, which follow a pattern set by the chirp mass mc equals m1 m2 to the 3/5 divided by m1 plus m2 to the 1/5. This value is the most precise indicator. Determining the mass ratio, precession, and spins is more complex. A significant factor is the effective spin chi-f, defined as the average projection of spins onto the orbital axis weighted by their contribution. A consistently positive effective spin hints at aligned spins and potentially an isolated evolutionary path. Conversely, a random distribution suggests that the pair formed through dynamic interactions.
While eccentricity effects are typically minimal by the detection time, efforts are made to find them. The presence of unusual harmonics would signal a recent close dynamical encounter. The accuracy of pinpointing the source in the sky is enhanced by using a network of detectors. With 3 or more observatories, the search area can be reduced to tens or hundreds of square degrees. These dark sirens, even without emitting light, can statistically calibrate cosmological models. This is achieved by correlating volumes containing galaxies with their respective catalogs, offering another method to derive cosmic data directly from gravity. Fact 81. What is called the photon ring differs from the thick, luminous band visible in shadow images. The ring we observe is actually the combined radiation from the accretion disk and corona spread out by turbulence and the interferometric aperture. The actual photon ring is composed of different subrings. These subrings are formed by light rays that have circled the black hole once, twice, 3 times, or more, each contributing a fainter and thinner signal than the last. Theory suggests that the brightness will decrease almost geometrically, and the width will shrink exponentially with each successive subring. The shape and position of these subrings are affected by the black hole's mass, spin, and orientation. Detecting them requires extremely long observational baselines and frequencies that reduce interference from interstellar scattering, as well as accurate closure phases. This will result in distinctive nulls and a comb pattern in the observational data. By detecting these subrings, the shadow will evolve from a mere visual representation into a precise measuring tool for Kerr geometry, allowing us to differentiate between the effects of plasma and the effects of pure gravity. Fact 82nd. Quasar microlensing functions as a natural scanning probe, allowing stars in the lensing galaxy to scan the background accretion disk. When a caustic traverses the source, various radii and sectors experience multiple amplifications. The relationship between disk size and wavelength, r of lambda, is recovered from the flash's color and temporal signature. The Shakura-Sanyaev thin disk model predicts r to be proportional to lambda raised to the power of 4/3. Yet, observational data frequently indicate larger dimensions and gentler temperature gradients, suggesting the influence of scattering, the corona, and irradiation. Occasionally, a caustic isolates a reflected component, causing the K-alpha iron line to shift and distort, akin to localized illumination at the inner rim. This effectively creates a laboratory for studying relativistic lines across cosmological distances. When used with polarimetry and continuum time delays, this technique provides unique insight into the disk and corona's two-dimensional structure without needing spatial resolution, as gravity itself maps the luminous region around the event horizon. Fact 83rd. Not every star orbiting a supermassive black hole faces a luminous tidal tearing. The concept of Hill's mass exists. If a black hole is excessively massive, its tidal radius lies within the event horizon, leading to the star's engulfment without any electromagnetic display. For a non-spinning black hole, this limit is roughly in the range of tens to hundreds of millions of solar masses for a star similar to our Sun. A fast spin and a prograde orbit can elevate this limit, creating opportunities for the disruption of even more massive celestial bodies. In contrast, when an intermediate mass black hole interacts with a white dwarf, exceptionally intense events are anticipated. The compressed, dense star could endure a thermonuclear explosion during the disruption, resulting in emissions in the gamma-ray and X-ray spectrum. Partial tearings occurring on elongated orbits can also happen, producing recurring smaller bursts. The observed population of tidal disruption events, TDEs, closely matches these limitations. The most massive galactic centers exhibit fewer flares, with spin and orbital geometry acting as unseen orchestrators of the outcome. Fact 84th. The paradox of youth in the galactic center concerns how O and B stars manage to form in a region where a black hole's tidal forces should prevent their assembly. Disk structure observations provide insight. At a certain stage, a substantial amount of cold gas entered the core, leading to the formation of a self-gravitating ring disk within its plane. This disk subsequently cooled, developed instability spirals, and fragmented into stars very close to the event horizon. This process yielded an initial mass spectrum with an abundance of massive stars, aligning with predictions from models of dense, irradiated environments. Evidence of this scenario has also been observed in other galaxies, appearing as maser-Keplerian disks and infrared rings located tens to hundreds of parsecs away from their centers. Another possible mechanism is the arrival of a compact young star cluster that drifts towards the center due to energy loss from friction. During this inward movement, some stars are elongated by tidal forces, while others persist on extended orbits belonging to the S family. These two mechanisms can operate concurrently, explaining how star formation can occur at the very edge of a gravitational void.
The 85th fact states that the corona surrounding an accreting black hole is composed of hot, ranging from tens to hundreds of keV, electron-positron plasma. Within this plasma, soft photons originating from the disk experience repeated Compton scattering, which shifts them towards a high-energy tail. The temperature and optical thickness of this corona are not random. When compactness is high, quantified by L equals LO sigma Q divided by RMEC cubed, there is an avalanche-like generation of E plus E pairs. This process leads to an increase in optical depth and cooling, a phenomenon termed the pair thermostat. As a result, the spectrum exhibits an exponential cutoff at energies approximately between 50 and 200 keV, a feature consistently detected by hard X-ray observatories. During flare events, this cutoff shifts, suggesting changes in the corona's altitude or density. The precise geometry of the corona continues to be debated, with proposed models including a compact lamppost structure above the axis, the base of a jet, or a flattened sandwich corona situated above the disk. Information derived from polarization, reverberation lags, and reflected components collectively indicates that the corona is compact, spanning a few to 10 gravitational radii, abundant in pairs, and probably plays a role in the magnetic energy processes of the jet, thereby linking the microphysics of pairs with the macrophysics of jets.
Fact 86th. The cosmic censorship hypothesis posits that singularities, should they form, are concealed behind the event horizon. In theory, one might consider overspinning a black hole, imparting a spin beyond the Kerr limit, or introducing a charge. This action could lead to the horizon's disappearance, revealing a naked singularity. Established thought experiments, beginning with Wald's argument, indicate that nature presents obstacles. Particles possessing the required parameters either fail to reach the horizon or, due to back reaction and radiation, thwart the attempt. Comparable findings emerge from calculations that incorporate gravitational self-interaction and superradiance. The system effectively defends itself by blocking trajectories that result in the parameter A star than 1. Within astrophysics, magnetic and photonic feedback from accretion further contributes. Accretion disks and coronae extract angular momentum with greater efficiency than they build spin. Observational data also does not show any naked objects. Pictures of the shadow, spectral signatures following mergers, and the lack of persistent optical or X-ray surfaces align with the presence of a horizon, though definitive proof for censorship remains elusive.
Fact 87. The tidal disruption of a star is not a sudden splash into a disk, but a sequence of shocks and orbital mechanics. Shredded gas streams initially return to their closest point to the central object along stretched ellipses. Due to general relativity's precession, their apsides are offset, leading to direct collisions that generate internal impacts, known as stream-stream shocks. When precession is significant, the gas quickly becomes more circular, and X-ray flashes occur instantly. If precession is minor, the gas remains in elongated orbits for an extended period, releasing energy at a greater distance from the event horizon. In such cases, optical/UV light and strong stellar winds become dominant. The black hole's spin and the orbit's inclination dictate the geometry, including potential energy dissipating points away from the center. Spectral lines of helium and nitrogen, along with bow-shock fluorescence and wide asymmetric profiles, provide information about where heating occurs. Radio emissions sometimes signal a jetted state. Warm dust creates an infrared echo, which helps map the three-dimensional configuration of the event. Overall, tidal disruption events, TDEs, serve as a laboratory for studying not only gravity, but also the nonlinear gas dynamics of circularization in a high-intensity field.
Fact 88. A thin disk does not huff with Newtonian viscosity. It generates noise through the bulbous-Hawley magnetorotational instability. A weak magnetic field within a differentially rotating gas links neighboring rings like springs. The inner ring pulls the outer one ahead, losing negative angular momentum and moving inward. The outer ring decelerates, carrying the moment away. Following this, a turbulent cascade engages, and the midplane transport is better described by the parameter alpha, which signifies effective stress relative to pressure. Yet, alpha is not a universal constant. Its saturation is contingent on the field's topology, especially on the existence of a net vertical flux. A high magnetic flux causes the disk to enter the mad state, where accretion is blocked by the field near the horizon, and the jet becomes stronger. A low flux leads to the sane, standard and active state, characterized by weaker jets and a more diffuse corona. GRMHD simulations incorporating light transport replicate observed spectra, polarization, and variability, implying that powerful radio galaxies and blazars indeed utilize disks with substantial magnetic flux, serving as the batteries that fuel the Blandford's-Nyjek process. Fact 89th. The distinction between a black hole and a pseudo-hole with a solid surface. Should an object lack a horizon, any matter falling onto it would be expected to stop and warm its surface, radiating heat. This effect is especially pronounced in quiescent phases when the X-ray corona diminishes. Observations reveal that quiescent black hole X-ray binaries are significantly fainter by orders of magnitude than neutron stars when the matter supply is comparable. This strongly suggests energy is lost beyond the horizon without any thermal reflection. Further evidence arises from the lack of consistent surface lines or flares, such as thermonuclear bursts, and from analyses of shadow maps. The contrast and dimensions of the shadow align with a gravitational shadow rather than an emitting shell. Searches for echoes in gravitational waves, meaning repeated signals after mergers that might originate from a reflective shell, have not yielded stable results, although current constraints are not definitive. While the combined arguments are strong, it must be acknowledged that these are empirical, negative proofs. The ultimate determination will depend on more precise shadow mapping, polarimetry, and ring-down spectroscopy. The 91st fact is that not all massive stars end their lives with a brilliant flash. Some are thought to collapse quietly, termed failed supernovae. In these events, the core collapses, producing a weak shock wave, and the star's outer layers partially fall back inward. This process results in the formation of a black hole with a minimal initial impulse. Supporting evidence comes from observations of red supergiants that vanish with little trace, as well as faint transient events showing brief envelope expansion followed by silence. The demographics of binary systems also offer clues, revealing massive components in tight orbits that lack obvious signs of a powerful impact. The likelihood of this scenario is influenced by metallicity and rotation speed. Stars with lower metal content lose less mass via stellar wind and tend to retain their massive cores. Fast rotation and close binary interactions can lead to a common envelope phase, speeding up the convergence of future black holes. The initial kicks during these collapses are less significant than those experienced by neutron stars, which aids in the survival of binary pairs until they merge. This composite view, drawn from disappearing giants, quiet transient events, and gravitational wave merger statistics, illustrates an alternative route for the creation of black holes. Fact 91. Gamma-ray bursts, the most powerful cosmic flashes, are frequently associated with black holes acting as engines. Long GRBs, exceeding 2 seconds in duration, are believed to originate from the collapse of a fast-spinning massive star. This process involves the star's core collapsing into a black hole, around which a hot accretion disk forms. Magnetic fields then initiate a narrow relativistic jet explained by mechanisms like Blandford's Nyack. Short GRBs, lasting under 2 seconds, are likely outcomes of neutron-star mergers or a neutron star with a black hole. Within milliseconds of such an event, a compact black hole with a disk and outflows also emerges. The estimated isotropic equivalent energies range from 10 to the 51 to 10 to the 54 ergs. Following the initial gamma-ray needle, an afterglow appears, spanning from radio to X-ray wavelengths. Shock waves interacting with the interstellar medium generate synchrotron radiation, while a jet break in the light curve signals a narrow collimation. Short bursts often exhibit a kilonova, an optical infrared emission resulting from the decay of R-process elements in the ejected matter. Fact 92. The dynamics of multiple systems serve as another matchmaker for stellar mass black holes. In hierarchical triple systems, the Kozai-Lidov mechanism increases the eccentricity of the inner orbit when the outer orbit is tilted. This leads to a shrinking pericenter, and gravitational radiation causes the pair to merge within the universe's age. Such a process naturally results in mergers with residual eccentricity at high frequencies and with chaotic spin orientations, contrasting with the evolution of isolated systems where spins are typically aligned. A comparable effect occurs in nuclear clusters near a supermassive black hole. It acts as an enabler, driving binary black holes to a catastrophic merger via secular resonances. Observationally, this is identified by low effective spin values, XF, and by subtle harmonics in the gravitational wave signal, which are sensitive to eccentricity. The overall scenario suggests that multiple channels operate concurrently, and the statistics of observed events gradually clarify their respective contributions. Fact 93. Astrometry has opened up a stealthy pursuit of nearby black holes. When an invisible companion tugs a star into a small elliptical path in the sky, precise position measurements will capture this dance. Unlike traditional X-ray binaries where accretion makes the object visible, in these cases the companion might barely feed and stay unseen. The integration of astrometry, radial velocity data, and photometry determines the mass of the dark object and excludes a luminous companion. These systems are significant for two main reasons. The first is to calibrate demographic data. It helps ascertain the number of stellar mass black holes around the Sun and their distributions by mass and orbit. The second is to reveal birth kicks. By analyzing spatial velocities and orbital inclinations, one can infer whether the collapse was silent or involved an asymmetrical blast. This technique enhances microlensing and X-ray astronomy, bridging the gap between the galaxy's noisy and quiet black holes. Fact 94th. Black holes are indirectly involved in the cosmological distance ladder. The luminosity of quasars, which are lamps fueled by accretion onto supermassive holes, makes them useful background beacons for gravitational lensing by galaxies. When multiple images are present, the source's variability reaches them with different time lags as the path and gravitational potential vary. Measuring these time delays and building a lens model allows for the determination of geometric distance and an estimation of the Hubble constant, known as the time delay method. This method is sensitive to the mass along the line of sight and to stellar microlenses, which, by the way, scan the quasar's accretion disk, yielding data on its dimensions and temperature profile. This creates a unique combination. A black hole functions as a light source for measuring the universe's scale, and microlenses act as a complementary zoom. Despite considerable systematic errors necessitating precise calibration, this method has established itself as an independent cosmological test, comparable to supernovae and the cosmic microwave background. The 95th fact concerns the era of black holes, which is the far future of the universe, a time when stars will extinguish and galaxies will disperse. Stellar mass black holes are estimated to evaporate via Hawking radiation over periods ranging from 10 to the 66th power to 10 to the 68th power years. Supermassive black holes will take even longer, a fantastic 10 to the 99th power to 10 to the 101st power years or more to evaporate. The greater a black hole's mass, the lower its radiation temperature. Evaporation is suppressed as long as the cosmic microwave background radiation is warmer than the black hole's temperature. Only after the background cools will the slow process of mass reduction commence. Theory suggests that the terminal phases of small object evaporation will involve a rapid surge in power and the release of high-energy particles, though precise details are still debated due to uncertainties in quantum gravity. A fundamentally different outcome is also conceivable if dark energy were to change or exhibit dynamic behavior. It is accurate to state that, based on our current understanding, black holes are the most enduring structures in the universe, and its final light will likely originate from their ultimate quantum whispers. Fact 96th. Theory predicts that stars around a supermassive black hole should arrange into a cosmic anthill, a sharp density concentration toward the center. For the simplest case of identical masses, this is the well-known Bacall-Wolf cusp, where stellar spatial density rises roughly as r to the -7/4. Actual galactic cores are complex, containing multiple components. Heavy remnants like black holes and neutron stars, due to mass segregation, migrate inward, creating an even steeper, dark cusp. Lighter giants and dwarfs, conversely, are distributed more gently. Observations of the Milky Way center present a nuanced challenge to standard models. Red giants appear to be depleted near SGR-A star, suggesting their outer layers were stripped by collisions and tidal forces, with the actual cusp concealed within unseen remnants. Indirect indicators, such as transient bursts, the distribution of X-ray sources, and hypervelocity stars, support the concept of a dark core. The cautious inference is that the theoretical cusp likely exists, but its visible pins have been eroded by evolution, leaving behind a gravitational imprint rather than a light-based one. Fact 97th. The disks around active nuclei serve not only as feeding grounds, but also as matchmakers for stellar mass black holes. In dense viscous gas, individual black holes get trapped in the disk's plane. They lose energy due to friction, form pairs, and move towards high-pressure regions, acting as traps where collisions are inevitable. The gas tori align the orbits and spins of the black holes with the disk's normal. This raises the probability of achieving a high effective spin chi-f greater than 0 and merging within short cosmological timeframes. Prior to a merger, the surrounding gas might emit weak electromagnetic radiation as quasi-periodic oscillations. Following the merger, an afterglow is observed. The newly formed black hole, by breaking through the disk, generates shock waves and temporarily boosts accretion. Detecting these events is currently debated because the signals are faint and can be mistaken for the natural variability of quasars. Nevertheless, the mechanism for producing mergers is physically sound and predictable. It naturally leads to mergers at Z to 1 to 2, allows for multiple hierarchical mergers, and potentially links gravitational wave signals with infrequent, dim optical and X-ray flashes. Fact 98. Gravitational waves, similar to light, can be bent by massive objects in their path. With strong lensing, a single chirp signal would reach us in several copies, delayed from seconds to days.
Detectors would observe repeated events featuring the same masses and wave patterns but varying amplitudes. At smaller scales, stars and black holes in the lensing galaxy microlens the signal, making its amplitude dependent on frequency, which results in spectral interference peaks. These phenomena are not just theoretical concepts, but anticipated, albeit infrequent, occurrences. The universe at significant redshifts contains numerous lenses. Investigations are carried out using merger catalogs. Consistent parameters and distinctive signal modulations would act as a lens signature and allow for fine-tuned cosmological measurements. Although concrete examples are still lacking, current limits are already impacting intriguing areas. If lensing effects are confirmed, we will acquire an additional tool for tomographic mapping. These same black hole mergers will function as markers for mapping mass distribution along the line of sight, covering everything from galaxies to their star clusters.
The 99th fact. Black holes are a proving ground for concepts of holography and dualities between fields and gravity. Within certain strict models, like anti-de Sitter space, a black hole's dynamics mirror the thermal evolution of a quantum field theory lacking gravity at its edge. The entropy of the horizon matches the count of microstates. The post-merger ring corresponds to the poles of correlation functions, and horizon currents are represented in fluid dynamics equations, fluid-gravity correspondence. The well-known viscosity ratio E over S equals H over 4 pi kb derived from these theories is unexpectedly similar to values for strongly interacting quark-gluon plasma observed in accelerators. These points do not concern specific celestial quasars, but rather fundamental principles: how quantum randomness is encoded by the horizon's area and how information is transformed into thermodynamics. A consequential, though indirect, benefit for astrophysics is the unification of black hole thermodynamics and statistical physics into a cohesive, mathematically precise framework. This framework serves as a reference for verifying both astronomical observations and experimental simulations. 100th fact. Single black holes drifting through interstellar space are almost impossible to see. When they lack a donor star or a thick gas cloud, they consume matter using the Bondi-Hoyle mechanism. This involves scarce gas and dust particles moving at speeds of tens of kilometers per second. For black holes with masses roughly 10 times that of the Sun and with a medium density of about 1 particle per cubic centimeter, the rate of matter intake is tiny. Additionally, in hot, thin gas streams, the efficiency of radiation is low because much of the energy is transported inward by advection, failing to turn into light. As a result, their expected brightness is a tiny fraction, less than 1/1,000,000th of the Sun's, usually manifesting as faint radio signals or hard X-ray emissions. This is why they are searched for differently: by observing the microlensing of stars, by tracking the slight movements of nearby objects, astrometric wobbles, and by detecting rare, brighter moments when they meet dense clouds. Upcoming large-scale radio and X-ray surveys, along with accurate astrometry, should systematically find these wanderers. This completes the cycle. From brilliant quasars to quiet, solitary black holes, their entire existence is understood through gravity, with light being just a frequent but not essential indicator of their presence.